So I'm in the electrical and computer engineering and computer science department here at UCF. And um, this is my group, right? So in addition to the Autonomous and Intelligent Systems Lab, I co-lead the Unmanned Autonomous Systems Lab joint with CAE, and that's a project ongoing with Dr. Zihoa Chu. My interests are generally in dynamical and network systems, optimization theory, and fundamentals of machine learning, particularly applying all these things in communication constrained environments and looking at how we can apply techniques we develop to cyber physical systems. So far at UCF, I've taught courses in linear control at the undergraduate and graduate levels, linear systems theory, nonlinear digital control. And I want to acknowledge, my sponsors and group members. I should point out that the student on the far right is actually a Ph.D. student in the math department, but over half of his work is, done with me in my group. We're talking about cyber physical systems today, and they are systems or devices in which we have sensing capabilities, decision-making capabilities, information processing capabilities embedded, right? And cyber physical systems are also systems in which there is that link between the physical environments in which they interact and the virtual or cyber piece in which a lot of the computation happens. One underlying think of it as a lubricating oil to make cyber physical systems work well is information, right? Information is communicated and relayed, information is processed, and information is used to make a control or actuation decisions, right, to make the systems work. What are these cyber physical systems, if you may? They are things like the power grid, right, in which, especially with the rise of renewable energy and all that, we have, we think of it as a safety critical system. We have self-interested agents. And I think we saw in the news not too long ago, possible adversarial behavior, right, at different levels, the physical devices themselves, or perhaps at the virtual or computation level on all of these. There are also systems that are becoming more integral in our urban type environments, sensing traffic, figuring out where there are pockets of people or people are gathering, using them to determine when street lights should get on, or when the trash needs to be taken out, or where to deploy the city resources. So that's another context or example. And another typical system we think of as the cyber physical systems have defense applications, right? So these unmanned autonomous air vehicles or ground vehicles, multi-domain type operations. And recently, I think this was last year, and there was an item of the news about the Army trying to test about 40 of these drones, like in real life. 40 doesn't sound like a lot, but I can bet you getting even just a handful of these devices to behave the way you want them to in real environments isn't the easiest of tasks. And so the goals of my group has been to develop computationally fast algorithms that are scalable, operating on a distributed architecture, all working in an information efficient way. As you'll see, the underlying theme of what I'll be presenting today is information communication efficiency. Another piece of all of this is being able to quantify uncertainty, even if we were to use a so-called machine learning or AI agent to make decisions. We want to know when that agent knows for a fact the level of confidence it has in the decision it's making. And this is all in the drive to integrate learning into control, right, at deeper levels. Okay, let's start out with a project on adversarial optimization. So the context in which we're operating is a network of sensors, UAVs, whatever we think of as them, in which a couple of them or more could be adversarial. What we want to know is the typical algorithms that are used to solve these kind of problems, how well would they do in the presence of adversaries? And we're not necessarily looking at, the network structure of how we can partition the graph to maybe cut the two red or bad guys off and things like that. We just want to go back into the information sharing domain and then ask how the effects of these adversarial agents on the network. So we'll think of the network objective as characterized by some function. Convex function, usually that can be any task we might want. It's always possible to describe such in that way. The agents carry out a simple update, right? Taking the gradient is a very common method used in this context, but the adversarial agents have a perturbation that they are adding to their updates, right? So when they add these perturbations, what recourse do the other agents have, and how well or how bad would the solutions be? Well, the approach is to have the agents compute an appropriate weight, taking into account information being received from their neighbors and, their updates, their information. And after doing the analysis, we find that the agents, the average of all the different agents, good and bad, will only come so close, right, to the optimal solution. How close do they come? Well, it depends on two important parameters. Not only does it depend on the size of the attack vectors that the malicious agents have, but also on the distance between the initial agent estimate, right, and the optimal point. If we want to see what this looks like in reality or via simulations, we can see that on the graph on the left, you have a little bit of an error, right, in this obtained value on the left-hand side, compared with the right-hand side where you have more adversarial agents. So yes, if we have more adversarial actors, we would get a little bit worse outcome. But an important takeaway from the analysis that was done in this work is the fact that we can still obtain reasonably good solutions, right, if we indeed pick the starting point of the algorithm to be no more than epsilon away from the optimal solution. So if this condition is violated, we found in the analysis, the convergence, right, blows up, it diverges. And we're able to take the outcomes of this work and apply in another setting where we modeled a distributed denial of service type attack. And that got, published last year in a journal. Another area my group is working on is in contagion dynamics, right? And the goals here broadly to develop what we think of as richer computational models describing, contagion processes or spreading processes generally. This is not just necessarily epidemics or bad things. It could be information flow in network systems. But in the context of epidemic, we know that the typical compartmental models, susceptible, infected, susceptible, recover type models are not sufficient anymore to really describe how diseases evolve, right? Specifically, we know that a bunch of activities that folks in the population take can affect the spread of those diseases, and we want to, from what we know people do, develop what we believe are optimal countermeasures, right? Keeping an eye on the disease spread data and learning, right, from the effects of the countermeasures we're taking, and trying to control the trajectory of these spreading type processes. Some of this work has been published with Shaurya Agarwal in the civil engineering department, and we attempted to pull a bigger team together, and conversations are still on to pursue some big NSF opportunities with Zishan Shuai in the math department and Taj and Griffith Parks in the biomedical sciences. So they are the biologists that bring in another angle of taking into account the genome. And some of this work broadly was also done with an undergraduate student in the CRCB REU program that Mubarak Shah runs. And that is taking an approach in which we may not even care about a model. So let's assume we don't want to spend all this time figuring out what the right spreading model is, but we say we want to learn what good controllers will be, right? How well can we do? Obviously, the approach in learning here is not, data-driven in the traditional sense, because we don't have the leeway to just test out things and see what happens. We're dealing with lives here. So we're taking a reinforcement learning type approach, right, to solve this problem. And the optimal actions we're proposing are also taking into account some of these factors without necessarily having knowledge of a ground truth or model. More recent efforts in my group has been in the area of distributed sensing, again, in communication constrained environments. So the work here is an offshoot of some work done with Dr. Chu that was sponsored by CAE. That separate CAE project is ITAR controlled and all that, so I can't share very much about that. But the goals were to develop and describe the impact of information availability, right, on distributed sensing. And as we'll see, we can always compress information to very few bits, enabling these techniques to work in stringent communication environments. So we have an environment in which there are mobile targets. The dynamics of those targets are noisy. And we have a bunch of sensors that we want to group together, have cooperate to solve the sensing problem. The goal of the sensors are maybe to estimate the trajectory or heading of these mobile targets. And each sensor here is computing an estimate of the process, of the dynamics of these targets, and sharing that information with neighbors. But because we're saying it's a communication constrained environment, all they're able to share are compressed or quantized versions, right, of the estimates. Again, the measurements they are making are also noisy. So we have a noisy process, noisy measurements, and somehow we're expected to cooperatively get high fidelity measurements, estimates of these dynamics. How do we do this? Well, we can find the right parameters to tune so that the estimates these agents are getting by sharing compressed versions or quantized versions of their measurements with their neighbors, each of these sensors can improve, right, its estimate of the dynamics in question. We're able to demonstrate this on a simple network or simple graph. Here we have 5 different sensors, all ranked in order. So sensor 1 is the best, 2 is the next best, 5 is the worst. In the simulations, we find a couple of interesting things. By changing the structure of the network at time 200 and maybe time 400, essentially changing the original network topology from this to on the right-hand side, we see that the performance, right, of these sensors reasonably significantly improves, right? So we can optimize the network topology, the interaction between these sensors, and also find the right tuning parameters to, reduce the uncertainty, right, in the estimates of this. One beautiful thing I really have to mention about this is the fact that these sensors need not be homogeneous, right? So LiDAR, radar, multi-sensor fusion, but we're focused here not on the sensory data. Instead, we're focused on the quality, right, of the estimates obtained. So there are many things that can be taken away from this. It's a scalable architecture because sensors can be added or removed. We know that the more sensors you add, the better the outcomes will be, especially if they are good sensors, right? So we're able to demonstrate some of these things, and it's a work that's feeding into the recent major NSF project that is ongoing here on smart streetscapes. We want to be able to use sensory data processed, right, for resource and asset management, right, in these smart streetscape context. And because of the applications here, the notions of privacy and fairness would necessarily come into play. Another thing of interest that's a little bit ongoing at this point, we're at the preliminary stage, is leveraging this process sensory data for optimization or for decision making, especially in discrete context. When you have finite numbers of things and you're counting, it becomes very tricky. And then in this same context, again, we want to use low resolution data, right, for inferences. My interests still remain at the intersection of, communication and control, taking into account other constraints that can be there, and then bringing in a little bit more real-time data analytics, right, into decision making. And of interest is looking at how all these fit into in environments where, that are uncertain or unknown, complex environments, and building more robust models in the distribution sense. and in the process, figuring out causality in AI algorithms. So we know that AI algorithms can make predictions and all that, but we really want to understand why and how those predictions are coming into play. There are a few opportunities we're pursuing, like currently, some of them this shorter term, other ones a little bit more longer term, and it'll be nice to see how some of these theory plays out in real physical systems. So collaboration will be of interest in validating these things and working with those in the AI space as well. And in addition to my PhD students, I'd like to acknowledge sponsors of this work. Thank you very much. I'll take questions.